today we're going to talk about measurement biases in educational assessment. So why is assessment important for teaching? So students work on assignments, home assignments, class assignments, and we can think of every mistake as a learning opportunity. We can then use the feedback to shape the learning process. This is called formative assessment. Formative assessment sets the learning objective. It paves the way of achieving it. It measures the progress utilizing a scoring criteria, which we call rubric. And then the student receives a feedback they can learn from. So the problem is that human assessment is a bottleneck. Checking assignments is time-consuming and cognitively demanding task. It takes lots of time distilling correct from incorrect, from subtle differences in the text. Assessment across different teachers can be inconsistent and many times include bias. We really want the AI to do it for us. If the AI can do the assessment part, then teachers will be more available to teaching. But can general-purpose AI do it well? Models like ChatGPT, Claude, Llama, we all know the buzz. The problem is their output is inconsistent. They are not aligned with the teaching goals. The input is just text with no additional context. And they interpret the scoring criteria, the rubric, differently from the teachers. So this makes the human experts labeling work, which is ground truth for these models, a bottleneck for AI alignment with education, with pedagogy, which is the theory and practice of teaching. So let's set a common language for the next few slides. So what are language models? These are mappings from the natural language space into a high-dimensional vector space. The input is free text. It could be a word, a sentence, a paragraph. It is then fed into a neural network, processed one layer after the other, and goes out at the other end as a vectorized representation of the text, which we call embedding. Embeddings encapsulate the semantics of the input text. Now, generative models work similarly, but in the opposite direction. So they are a mapping from the vector space back into the natural language space. So green arrows are for embedding models and yellow arrows for generative models. We will say the two sentences are semantically similar if they carry similar meaning. For example, I enjoy music and I love listening to music carry similar meaning. Their vectorized representation will lie closely in the vector space. Whereas for dissimilar sentences like I enjoy music and I lost my keys, their vectors will have a large angle between them in the vector space. So, seeking ways to scale, we therefore investigate first the embedding space. The data we use are answers of high school students to open-ended questions in biology that share the same rubric, scoring criteria. And we compute the pairwise similarities of all pairs of answers that exhibit the same type of errors and all pairs of answers that exhibit different types of errors. To foreshadow the results, we found a strong correlation between the correctness of the student answers and the ability of the language models to correctly interpret them. The vectors of the correct answers are highly similar in the vector space. Whereas as the lower the knowledge level in the answers, the less similar to each other the vectors are in the embedding space. This correlates with the famous quote from Tolstoy's novel, Anna Karenina, that all happy families are alike. Each unhappy family is unhappy in its own way, where we identify the correct answers with the happy families and the incorrect ones and the partially correct with the unhappy ones. We named it the Anna Karenina principle of automated assessment. If you look at the illustration on the side, so this is not real data, just demonstrating intuitively the results. The vectors of the correct answers are the black circle at the center, danced together in a ball-like shape, where the partially towards the incorrect answers drift further and further away as the correctness decreases, or the knowledge level decreases. On the left, you will see visualization of the real data. You can see the darker blue dots are for the correct responses, pretty tight together. And for example, if we look at the light blue, which for the totally incorrect responses, they drift at the edges of the scatter plot. This is visible also in the top table. The arrow direction shows the decrease in similarities as the knowledge level decreases. So higher index in the title shows lower knowledge level. We also found that for answers that exhibit the same type of error, they're actually more similar to the correct, their vectors are more similar to the correct answers than to their own type. This is supported in the bottom table, where you can compare the diagonal indicating the similarities of the same type of errors, and the top row is for the similarity to the correct answers, and we see the top row are consistently higher than the diagonal. We see a similar trend in generative models. We found that measuring the disagreement between scoring of AI raters with various generative models and compared it to human raters. So we compared human to humans agreement and AI models to humans agreement. We found high agreement on correct answers and on the totally incorrect, but poor agreement on the partially correct. If we look at the graph on the right, so the correct answers are just above the 10 here, and we see the convergence, the agreement of all the AI and human raters. On the left, we see relatively high agreement on the completely incorrect answers, and all of the middle quality range in between, we see this belly, the inverted U shape, indicating for low agreement on the partially correct answers. To conclude, so students' errors come in all shapes and flavors, but it sends a noisy signal to language models. The correct answers are consistently identifiable across all model types, human, AIs, generative, embeddings, where the erroneous answers in the embedding models, they are interpreted as different while sharing the same underlying cognitive error. And for the generative models, we see a large disagreement on the partially correct and on the partially correct answers. So this raises serious fairness concerns on AI feedback systems that utilize general-purpose AI models, as these are consistently misaligned with the educational experts on the partially correct answers and the incorrect ones. But these belong to the students that needs the feedback most. So our results imply that task-specific model adaptation is essential for getting an effective and fair feedback AI systems. I want to thank my advisor, Professor Georg Alexandron, who led the computational approaches to science education group in the science education department, and Dr. Beata Bigman-Klebanov that collaborate with us from the ETS Research Institute. Thanks.